We'd like to warmly welcome you for our site visit tour through our MCL. My name is Kerstin Kladil. I'm a Material Service Manager dealing with experimental methods. I will guide you through our laboratories.
My name is Silvia Leitner. I'm a computation materials scientist. I will guide you through our simulation group. Please take your time and enjoy our tour through the MCL.
At the beginning of our tour, I'd like to give our big boss, Professor Ebner, the possibility to say some words about his MCL.
Materials are a central basis of modern life. For instance, mobility, digital communication, energy supply or medical care, as we know them today, would not be possible without advanced materials and their technologies. Manifold applications in industries as diverse as aerospace, mechanical engineering or microelectronics place extraordinary demands on materials. But by understanding the relationship between chemical composition, manufacturing process, microstructure and operational behavior, it is possible to meet even extreme property requirements. The Materials Center Leoben has been conducting cooperative materials-related research for more than 20 years. Our main focus is to combine the experimental methods that we develop in our laboratories with simulation and modeling at all relevant length scales. We start with computer-aided materials design at the atomic level, we investigate and simulate production processes, and we conclude with the implementation of components into larger systems. In the following half hour, we will show examples of recently developed experimental and simulation techniques and how we use them in research projects. And now please enjoy the video.
This is Stefan Massona, head of the department's Materials and Services. Stefan, please give me an idea of the possibilities in our labs.
The MCL has excellent laboratory equipment and highly qualified and motivated staff. Our method portfolio includes both standardized tests, partly within the framework of laboratory accreditation, as well as special and high-end tests within the scope of scientific projects. An important part of our activities is the materials and failure analysis of metallic and ceramic materials and composites.
The starting point for our lab tour is the metallographic lab. Comprehensive component or failure analysis start in this laboratory. Here we receive the components and samples, document them and prepare them for further analysis. Our staff works under the highest quality standards according to the requirements of the ISO 9001 and also ISO 17025 in the accredited area of the testing laboratory. Microstructure characterization as well as hardness tests give us the first opportunity to deduce a property. However, not only microsections are produced here. The material is prepared for all further high-resolution testing methods. In our scanning electron microscopy laboratory, we operate 4 high-performance electron microscopes. We cover fast customer orders for damage analysis to high resolution and in situ characterization. With the high-resolution analytical SEM, we realize magnifications up to 1 million times. The analytics allows us to study the microstructure and local chemistry of the samples with a resolution of a few 10 nanometers. We use ion beam milling to cut slices for tomographic imaging of microstructures. In addition, we use the ion beam milling for the preparation of micromechanical samples. A modular SEM allows us to integrate different modules such as tensile test unit, a nanointentor, an atomic force microscope or a heating module. This allows us, for example, in situ studies of deformation phenomena or phase transformations. Currently, we are developing static and cyclic test methods with a nanointentor to determine critical shear forces at interfaces or fracture mechanical properties of grain boundaries. With all this equipment, we are able to understand the properties of individual phase components and interfaces in order to incorporate them into the modeling of new materials. Complementary to the 3D scanning electron microscopy, we operate the computed tomography. As a cross-scale method, samples from large components up to sub-millimeter can be examined for materials research. In the field of X-ray structural analysis, we determine different crystallographic parameters which are important for component analysis, but also for the validation of our computer models. This gives us the opportunity to design and validate properties at the crystal level. The precise control of the test position as well as a wide range of optics and anode materials allows us the greatest flexibility in testing to examine microelectronic components as well as powdered metallic and ceramic components and samples. Residual stresses have a great influence on mechanical properties. In particular, the fatigue behavior but also the sensitivity to hydrogen embrittlement depends on the residual stress profiles. For this reason, it is important to know the residual stresses at all relevant length scales. While the determination of residual stresses on the macro scale is largely standard, we focus our method development on the determination of residual stresses on the microstructure scale. For the determination of residual stresses on different length scales, we use sectional and X-ray based methods as well as Raman microscopy. We operate an accredited testing center for standard tensile and hardness tests, but also for fracture toughness and fatigue tests. Thus, the most frequently required mechanical material parameters can be determined according to the current ISO and ASTM standards, with the highest accuracy in a temperature range of -150 degrees C up to 1200 degrees C. Mechanical testing for our research projects meets a wide range of requirements. This includes the testing of a wide variety of materials, from ultra-high-strength, brittle hard metals to novel high-temperature material concepts such as high-entropy alloys. We test within a wide range of conditions with different atmospheres or vacuum. The temperature during static or cyclic testing is up to 1500 degrees C and down to -150 degrees C. Extremely complex load collectives, like for example in railway applications, need to perform multi-axial tests. At our multi-axial testing facility, we are able to perform such tests. We follow up our tour on the microelectronic department. In this department, around 30 employees are working on different topics of microelectronic issues. I'd like to introduce you to my colleague, the head of department, Elke Kraker.
Welcome to the microelectronics department. We are doing material research in the field of smart electronics with a special focus of green electronics. Let's have a look at our labs where we're doing research.
We develop coatings for energy-related systems and sensors in our thin film laboratory. The characterization of the thin films ranges from the determination of the film thickness, the chemical composition, the electrical properties, to the testing of the functionality of sensors. High temperatures in electronic systems are often the reason for system degeneration and reduced service life. Optimal temperature management increases the service life and saves natural resources. We experimentally investigate the thermal behavior of thin films up to fully assembled systems. These results are needed for the computational design and optimal thermal management of components. The fastening and long-term functionality of components on circuit boards requires sound connection technologies. We use destructive physical analysis to test the deformation, damage and fracture behavior of different assembly and connection technologies and evaluate the long-time reliability. The development of complete measuring units enables conclusions to be drawn about the origin of changes in order to ultimately determine the reasons for the failure of a system. With Marie, we developed a measuring unit for monitoring LED systems during live tests that links the change in the thermal path to the aging of the material. With this knowledge, the lifespan of LED lighting can not only be predicted but also significantly improved. Our test laboratories are well positioned and equipped, and our employees are highly qualified and motivated. Our goal is to compile highly accurate material datasets with continuously improved and developed methods to meet the complex requirements of our research projects.
In addition to our experimental capabilities, the Material Center Leoben is also very strong in simulation. We are now at the simulation department, where about 60 researchers work on computational materials design, smart manufacturing processes and product reliability. I would like to introduce you now to Werner Ecker, who is the head of this department. Werner, what are the challenges we deal with every day?
The key is to find the right model for the right purpose. The models we use at MCL are either ab initio or based on experiments or sensor data. Our USP is our vast material knowledge and the ability to combine physical-based with data-driven models. Like this, we generate highly accurate and fast models. With our simulations, we accelerate innovation processes, for example, for green mobility, microelectronics, and energy storage solutions.
The challenge in computational materials design is to combine simulations across all relevant length scales, from the atom to the component, in toolkits for several different applications. With the help of atomistic calculations, we get an idea how atoms interact with each other, how they form phases, and how they segregate at crystal defects such as grain boundaries. By the integration of these atomistic puzzle pieces in higher order models, like thermokinetic models, we're able to predict the material's microstructure and properties. For example, the MCL has developed the software tool SecroCalc, which allows optimizing chemical compositions and heat treatments for grain boundary dominated metals.
Our key strategy to further accelerating the material innovation process is to combine calculated and measured data with adaptive learning methods to material accelerator platforms.
But not only materials design, also the design of innovative and resource-efficient manufacturing processes is part of our research program. With physical-based and hybrid modeling, we develop digital shadows and digital twins of manufacturing processes. Applying these models in a forward manner allows to predict local properties in the components. By using them in an inverse mode, they deliver the correct process parameters to achieve target properties.
Our vision is to develop smart processes planning and control software.
With the reliability calculation and model-based condition monitoring, we extend simulation and modeling to the entire life cycle of technical products. The aim is to increase the service life of products by optimizing the property profile and by continuous condition monitoring. A good example for this is our software Inara. It incorporates advanced models for short crack growth to assess the influence of initial conditions and load sequence effects on crack propagation in railway axes. This assessment and maintenance planning tool is already in use at well-known companies across Europe. Regardless of the size of the product, we also develop models for material-oriented multiphysics simulations for microelectronic devices. One example is the thermal management of a microelectronic component, which is crucial for a long service life. Here, we simulate, for example, the effect of interfaces on the thermal conductivity.
We make components smart and products reliable.
Wow, what a great tour! We hope you enjoyed it.
Working at the MCL is great, it's exciting, new every day and never boring. There's just one more thing to say. We innovate materials.